Good afternoon, everybody. Today I am going to discuss the first order reaction. I have already discussed the zero order reaction in my previous class, and today I will tell you about the first order reaction. And I will try to deal with these topics like the integrated rate law, units of a first order reaction, and then half-life time and the lifetime and the average life of a first order reaction. And the most important thing is the graphs of first order reaction, because you will be having multiple choice questions and there are a plethora of graphs which can be framed from the equations of the first order reaction. And if time permits, I will take the examples of first order reaction. Otherwise, I will take it in a separate lecture, examples as well as some numericals also. And so let's come over to the first order reactions topic. And one thing more I have to tell you, that the first order reaction is the most important topic of your chemical kinetics chapter, and from multiple choice question point of view also, its examples, its graphs, its half-life, its units, and the integrated rate law, because many numericals are framed, many simple numericals, I can say many simple numericals are framed on first law. Okay, so from the multiple choice question point of view also, it is a very important topic and most interesting also. Okay, so now let's come to the first order reaction. So what is actually first order reaction is one in which the rate law expression depends on the concentration of only one term only. Okay, so let's take a very simple reaction, A forming products. So if we have to write the rate expression for this reaction, this is our reactant and it is forming products, A forming product. Now if we have to write a very simple rate expression for this, then the rate law will be how much? The rate law I can write R. This will be equal to the rate product of the rate constant K multiplied by the concentration of one reactant only. I have written this one. What is one? One is the order of the reaction, and since it is a first order reaction, I have written one over here, and simply raised to power 1 will remain A. You understand that much. Now let's take the differential form of the first order reaction. You have already stated, if the stoichiometry is 1, then the rate of reaction R will be given by minus, since it is being consumed, minus dA upon dt. This is our rate expression, and since the stoichiometry is 1, we can place 1 upon 1. Okay. I have not written it because it is quite understood that 1 upon 1 is always 1. So the rate of reaction is here is A, can be written in this form also, and the rate of reaction instantaneous, this is giving you the instantaneous rate of reaction. The instantaneous rate of reaction is dA upon dt. This implies the concentration, and this is our reactant concentration, and this implies the concentration square brackets. Okay. So let it be equation number 1 and let this be our equation number 2. And since both equation number 1 and equation number 2, they both are representing the rate of the reaction, so we can equate them. Okay. So let's equate them. What we get is that minus dA upon dt will be equal to Ka. A slight rearrangement over here, and what we get is minus. You remember, we are placing minus sign because in this expression, because A is continuously being consumed, the concentration of A is declining. This will be equal to K into T. Dt will come over here and A over here. K. Let it be equation number 3. Now this is our differential form of equation, and we need to integrate it, since it is giving the speed at a instantaneous speed, at any instant of time we are having this concentration. So we have to integrate it now, and for integration, suppose this is our reaction when the time is 0, t is equal to 0, then at any instant of time, let the concentration be A0. Okay? Then that concentration of products will be 0 at this instant of time. And suppose after time t, when a small amount of A naught is decomposed or it has reacted, suppose X amount of product has been formed, then at that instant of time, let the concentration be A. So our final concentration is A at any time t, after time t, and the initial one is A0. What does this A signifies? A signifies the amount that is remaining. Okay. Suppose 40% of the reaction has been completed, then 60% will remain. Okay. So this A signifies कितना amount बच रहा है, the amount remaining, because this is the point of maximum confusion when you are doing the numericals. So this A, this will signify the amount that is remaining after time t. In fact, it is A naught minus x. This A is actually, this A signifies A naught minus x. Because x we are taking here the concentration that has been formed of the products, and as we are seeing, the A is transforming to the product. So this is A is actually the remaining concentration. You can write it as remaining concentration, so that when you are revising your chapters, there is no confusion. Remaining concentration. Okay, this A signifies remaining concentration. A naught is our initial concentration, and T is equal to 0. So let's come over to this equation number 3, and let us now integrate it between the limits when between the initial and the final. Initial concentration being A naught and the final concentration being A0. So we have here dA. Let's write it dA. Okay, upon A, between the limits. Lower limit is what? A naught, and the upper limit is A. We will integrate it between these two limits. Is equal to, let's take minus over here. I have shifted the minus to this side. K dt. And here the lower limit is what? 0, and the upper limit is t. Okay, we are integrating between these two limits. So let it be equation number 4. Let it be equation number 4. So as we all know that when we integrate 1 upon x dx, if we integrate it, it is given by log natural x. And log natural, if we convert this log natural to base 10, log base 10, then we have to multiply it by 2.303. I will tell all this to you afterwards. So 1 upon x dx is given by, if we integrate it, it is given by log natural x. So we apply this formula over here, and what we get is that log natural A, lower limit A naught and upper limit A, this will be equal to minus K is a constant, and we have the T, lower limit 0 and upper limit A. Just to segregate it from this equation. Okay. Now let's solve this equation over here. So what we get here? Natural log upper limit minus lower limit log natural A naught. This is equal to minus K T upper limit minus lower limit is 0. So this is from that is equation number 5. So if we calculate it, this comes out to be log natural A minus log natural A naught will be equal to minus K multiplied by this T K, and minus this will come out to 0. So let's ignore it. So this will be our equation number 6. Now as we can see, This equation is very important. Equation number 1 is also very important from the graph point of view, and I will take these equations afterwards because there is no space. When I will be telling you about the graphs, then I will consider these equations once again. So we have this equation log natural A minus log natural A naught is equal to minus A. Now we know a very important property of log, that suppose we are having log of n minus log of n, then we can write it in this way, log of m upon n. You must be familiar with this relation of log, this property of log. So we will apply this property over here. What we see is that log natural, this is actually log natural A, and when we convert it to log base 10, it will become 2.303 log base 10. Okay. So log natural A minus log natural A naught is equal to minus of A. When we apply this property of log over here, what we have is log natural A upon A naught. A naught is our initial concentration and A is the concentration that remains after time t, is equal to minus A. So we will reverse this expression, and this is another form of this expression, and it comes out to be log natural A naught upon A will be equal to K. I have done this just to remove the negative sign. We will reverse it and it will be log natural A naught upon A. Now let's calculate what will be the value of K, the integrated rate law expression for a first order reaction. This will come out to be 1 upon 3 log natural A naught upon A. So this is our expression for a first order reaction. Sorry, this is our expression for a first order integrated rate law for a first order reaction. Here I would like to add a bit more, since in your books it is given in some other form. Let's consider this A formic products. Okay, A formic products. If A is the initial concentration, if small a is the initial concentration, as it has been given in your books, and at time t, when time t is 0, means initial concentration is A and the products are not formed, and after time t, suppose x amount of product is formed, then the amount of A that is remaining will be A minus x. So if we substitute these values, the amount remaining means A is A minus x over here, and the initial concentration is A, then our rate expression becomes 1 upon t log natural A upon A minus x. Actually it is given in this form in your book, but I think this is more simple and more easy to understand from your numerical point of view also. So this is also one of the expression for the rate law, and one more expression can be there when you change this log natural to log base 10. Then what you have is K will be equal to, the rate expression will be equal to 1 upon t 2 multiplied by 2.303. Since we are changing the natural log to log base 10, we have to multiply by this factor, and this will be log of A naught. So this is also one of the expression. And let me tell you about the units of this first order reaction. If we look over here, this is time, so it will be 1 upon time, okay, multiplied by log of A naught upon A. A naught is concentration and it will be in moles per liter, multiplied by moles per liter. Now we have this A in the denominator, and A is again the concentration and it is in moles per liter. So both these concentration terms get cancelled out, and what remains is 1 upon time, or we can say time inverse also. is equal to time inverse. So this is the unit for a first order reaction. Suppose you are given a first order, suppose you are given a reaction and the rate of reaction is given and the unit is given to be time inverse, then you can just in a second you can tell that it is a first order reaction if the units are time inverse. Okay. So now I will tell you about the half-life and lifetime and average life in my next